we were comparing our own galaxy with a couple of other spiral galaxies, we talked about certain comparisons. We saw at a picture edge on versus face on. So we have a pretty good idea. So because we're within the Milky Way galaxy, we can't take a picture of it because we'd have to go outside. So we can't really see our own galaxy edge on or face on. But we know a fair amount about our galaxy. We know, we're part of the disk. We have a lot of data. We know the galactic center is really bright in radio waves. So we have a lot of observations, and we also know that the halo is spherical. It goes around all over, and it has the more metal poor stars. It's all from mostly the spectral data. If you have spectral data and you don't see the lines missing for something, say for calcium, then you know that calcium is not within that star. So things like that, and it kind of also matches with our sort of understanding of how things evolve. So for example, the spiral galaxies have these big spiral arms. Let me get to the picture. In the big spiral arms, there are some hotbeds that we call of star formation regions. And those are pretty, those are kind of where I gotcha. I've been camping years ago and got a great view of the night sky without. Yeah, so if you go to somewhere dark, hopefully you can see the Milky Way galaxy. So this is our galaxy, an artist's impression of our galaxy. And let me real quick show you the pictures of two other galaxies. So these are images. So I don't know if you can see very well, but one of them is an edge-on image and the other is so this is an edge-on image and this is a face-on image. So these are actual images taken of NGC 891 and M83, and these are also spiral galaxies. Those kind of help us with the comparison of, I'll get to that question, but those kind of help us with other spiral galaxies as well. And then before I forget, let me answer about the galaxy collision. So we spoke about it yesterday, but I just want to summarize it. There's a really nice summary here, and this is the book, which is called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. Ooh, another picture I wanted to show you. So if two galaxies merge, sometimes this is sort of what it might look like, where the two galaxies are basically putting tidal forces on each other. And it's almost like catching hold of a tail, if you will. It's kind of like give me your tail, I'll take your tail. And then sort of the material starts to come together, merge more and more. It's like grabbing onto someone by the tail and slowly pulling each other in. And then that ends up being ends up being the merge of that galaxy. So what I just showed you is a recently simulated galaxy encounter. And we're going to do that sort of thing with Andromeda. So we talked about our merger with Andromeda. So let me quickly talk about that, because that was the initial question that Rouge 1 asked about the galaxy mergers. So here's a nice summary. So things to remember when galaxies do collide. Individual stars we don't believe will collide with each other. There will not be a sudden bonanza of blue stragglers. Galaxy collisions are inelastic. So remember the inelastic. So if there's two objects, inelastic collision is like when they stick together like this. Elastic collision is when they bounce apart. So galaxy collisions are considered to be, collisions are considered to be inelastic. That is, during the collision, some of the orbital kinetic energy of the galaxies is converted to internal energy in the form of random motions of the stars. Thus, a pair of galaxies that start out on a hyperbolic orbits relative to each other can still end up as a bound system. Yes. Yeah. We will be the Milky Way galaxy, and then we won't significantly merge with Andromeda. until about 3.2 billion years later. And then in 6 billion years or 6 giga years, we will have the merger with Andromeda. Next point about galaxy collisions is that although the stars don't collide, the gas clouds do collide within the galaxies. So a giant molecular cloud has a radius of around 10 parsecs. So that's around 4 times 10 to the 8, the radius of our sun, for example. And the large cross section for molecular clouds mean that the gas clouds will collide when two gas-rich galaxies pass through each other. Does time act the same here as other galaxies? So that's a great question. So according to general theory of relativity, it's really about where, if you're near a very massive object or not. So it's not so much about the galaxy, but are you near a very massive object, because that's going to bend space-time differently. Okay? Thanks to the colliding gas clouds, merging galaxies are hotbeds of star formation. So this is the main thing that you can expect when two galaxies collide, is that it will actually lead to new stars forming. So, even our sun came from a nebula, like the sun and the planets in our solar system came from a pretty enriched gas cloud. So the sun has calcium in it. So it's not a metal poor star. It's burning hydrogen to make helium. So it's doing a pretty basic nuclear reaction, but it also has other elements in it. How do we know? You would get spectral lines from something like the sun. You can look up spectroscopy, and pretty much if the energy is absorbed by a certain element, it will show up as a line or a missing line, an absorption line, basically. And that's how we know, oh, wow, so the sun actually has, for example, calcium. And from these spectroscopic lines, we would know. So that's because we come from, all of us, we are all coming from some gas cloud, which ultimately condensated to make the sun and the planets. And we actually talked about the planets a lot in some of the lives as well. So when we talked about planetology and how our solar system was made and planets and everything like that, and comparison of all the planets. So I had a number of lives on this a few lives ago. Then I got into galaxies. You will see that we talked about how different planets formed at different distances from the sun, but all of us kind of formed in the same plane, and we all orbit in the same plane and all of that, because we literally come from some nebula, and most of the mass of that nebula went to the sun. So 99.8%, but check my number, of the mass of that nebula went to the sun, and only 5% of the angular momentum went to the sun, and all the rest of the angular momentum is within us, the planets. So that's why the planets are rotating a lot faster, and a lot more of the angular momentum is within the planets. So, the gas clouds, it may sound kind of boring, like galaxies, gas clouds, but actually, first of all, did you also know that there's a lot of mass? There's more mass in gases than in stars. There's just a ton of gas, actually, in all of these galaxy. The edge of the universe stop growing. So there is no edge, actually. There is no edge that we know of in the universe. I just saw the question real quick, so I thought I'd quickly answer, and I'd get back to my the star stuff. But it's extremely important to appreciate, even though gas clouds and gases and interstellar medium is something we don't talk about too much, but actually that interstellar medium being enriched is very important. And in fact, this is why supernovae are important. When stars die, when they explode, what's happening is they're putting all their material that they just spend their whole life making. Like, for example, they could have burned hydrogen to helium like our own sun, or they could have made carbon and oxygen and further higher and higher, heavier elements. They could have if they have an iron core, then they have done a lot of nuclear physics, right, within their lifetime. And when they explode, there is a lot of material that's going everywhere in terms of the stellar winds. We talked about core collapse supernovae as well in the past. So there's more details in that particular live. But basically, sometimes during a supernova, the star will lose a lot of its material even before it has completely collapsed through stellar winds. And remember, all of these processes and ultimately the explosion and everything, shock accelerations and shocks with even the interstellar medium, is basically putting material into the interstellar medium. And why is that important? Because that will make metal-rich gas clouds, where in astronomy, anything above helium is a metal. So even if you made lithium, carbon, boron, beryllium, anything, nitrogen, we love it. Like in astronomy, we say that being metal rich is just having any element. Pretty much if you have significant elements over helium, then that's pretty good. That's metal rich. Why do we say metal poor? Because remember, the very old stars, the first generation of stars that were formed in the universe would be metal poor. Why? Because remember, we talked about cosmology, and we know that in the Big Bang nucleosynthesis, as far as baryons go, we just made hydrogen and a little bit of helium and very trace amounts of lithium. So the first stars did not have stars before that to help them have more stuff to begin with, more types of metals to begin with. They were literally happening from the baryons that were available back then, which was mainly just hydrogen. Even now, the most abundant element in the universe is just hydrogen. That tells you something, right? Which is that hydrogen is what you can expect in the universe. Like these stars don't have, the first stars, the population 2 old stars, those don't have a ton of metals. They would just mainly have hydrogen and maybe a little bit of helium. So that's what I mean by the metal rich, metal poor. But this is incredibly important. The merging of galaxies too is another way in which the interstellar medium can get more metal rich. And then the nebula that would form, and then that nebula would cool down and, make a new star and planets, maybe just like our solar system formed, something like that. Maybe something, not every time will be the same way, but that is incredibly important, because then that will lead to the future solar systems, future star systems, right? So even our galaxy will do that with Andromeda, and that will enrich our gases, our interstellar medium further. And who knows what types of star systems will form, what types of planets will form, and what types of aliens will live on them in the future, okay? So the class of galaxies known as ultra-luminous infrared galaxies are frequently found to be merging galaxies in which large numbers of dust-enshrouded protostars, so sort of like the beginning of a star, produce copious amounts of far infrared light. Merging galaxies also produce lots of blue and ultraviolet light, thanks to the large number of O and B stars produced. So these are pretty hot and happening stars. The merging galaxies, known as the antennae, attribute to their long tidal tails. So those tails I showed you in the picture just now,